thank you everyone for staying around. We've had a lot of seminars and presentations in the last week, and there's conferences at Wollongong and the Future Energy Conference the last 3 days, and now Ned and Gavin's symposium, which has been really excellent. So today we've got a slightly different perspective. We are going to talk about electrochemical capacitors, and we're very fortunate to have John Miller, who's president of JME Corporation. I've just asked John what JME stands for, and historically was John Miller Enterprises, but has been shortened to JME. He's also a professor at Case Western Reserve University in the US. So John's been visiting Sydney this week, mainly for the Future Energy Conference, which we had earlier this week, but he's offered to stay around today and give us a seminar, and today focusing more on use of electrochemical capacitors and their potential in the energy industry. So thank you, John.
Okay. Thank you for the nice introduction, and I want to thank University of New South Wales for inviting me to give a presentation today. What I will be talking about is a technology that's, I think, got great potential in the future for use in the electric utility industry. It's being used, I'll give some examples of being used today, but the presentation, I have an outline here of the topics I will be talking about. I want to give an introduction to the capacitors a little bit and compare it to other technologies you're more familiar with, and batteries is what I'll be using as a basis for comparison. Then I'll be talking about applications, energy conservation applications, and then some energy sector applications. And finally, I want to give just a very basic economics and then summarize here. So let me start by giving a introduction to the technology. And first of all, physical energy storage has a real advantage in that it is usually highly reversible. One example is gravity here, and that shows an example that is widely used now in the utility industry. In fact, it's the most common storage mechanism that's used. Perhaps 98% of the storage around the world is gravity. It's pumped hydro. Another one is kinetic energy, and that's rotation. Flywheels are being used. The electric field in a capacitor. Magnetic fields are being used. SMES is one example that has been looked for bulk energy storage. And finally, mechanical. And I heard earlier this week talks on compressed air storage. And that, again, is a spring that you're storing. It's a physical storage. And each one of these has potential, I believe. But the one I'll be talking about today is the capacitors. And that's got no moving parts. And it also is very highly reversible. And it stores energy electrically. That's one of the few types of storage that does not have conversion losses of going from one form to another form of energy. For instance, batteries go from the electrical to then chemical, then back to electrical again. So you get conversion losses. So the capacitor is one of the few technologies that does not have the conversion losses. So if we look at storage technology components, we can divide that into batteries and capacitors. And of course, in the batteries, we have the primary batteries and the secondary batteries. And in the capacitors, there's three major types: the electrostatic, electrolytic, and the electrochemical. And the electrostatic is one of the oldest types of capacitors. It's also the one that operates at the highest frequencies. This would be a mica capacitor, a film capacitor. It's generally used in applications where you do need that high frequency performance. Electrolytics is a more recent development, and that is used primarily for converting AC to DC. And aluminum electrolytics are used, for instance, in the laptop charger. All the battery chargers are using electrolytic capacitors. And the electrochemical is the one I'll be talking about today, and that is even more recent. And you could do either further divisions. Under the secondary batteries, we have different types. The lithium ion is the most recent, and that is one that is becoming very, very important technologically. And under the electrochemical capacitors, we have the symmetric and asymmetric. And further dividing the symmetric, the most important commercially today is the organic electrolyte symmetric electrochemical capacitor. That's the most popular. The original ones were aqueous electrolyte, and I'll talk briefly about aqueous electrolyte asymmetric capacitors for the utility grid, for day-night storage. And this is a very important technological advancement, the lithium-ion capacitor that is being developed, or has been developed, commercialized in Japan. So if we do a comparison of the different types of capacitors, we see that the electrochemical capacitor has much more energy, specific energy, than the other two types. But it comes at a price, and that price right here is shown by cycle life and the charge-discharge times. The high energy right here means that it has much less cycle life than the electrostatic and the electrolytic capacitors, and its response time is also much longer. It's about 1 second versus, for instance, electrostatic capacitors can be 10 to the minus 9 seconds. So if we look at this technology here, it's often called supercapacitors or ultracapacitors. And it's obvious the reason. It's got 100 times more energy per volume than conventional capacitors. It was invented in the 1960s by Standard Oil of Ohio, and it was commercially introduced in 1978 by NEC in Japan. So the first application, the original market, was a CMOS memory backup. This is for volatile memories. So it's essentially a DC application, and it was replacing at that time NiCad batteries, button NiCads that were quite unreliable. So this was important in the early days when it was introduced in 1978. In the 1990s, I think the appreciation of other attributes this technology had, especially its high power performance compared to batteries, especially on charging. It's very high cycle life, and typically this technology offers, as I showed, 1 million cycles. Very long operational life, and there's many applications you'll use it for 12 years. It's very reliable and very safe. It has no exothermic reactions. So it's physical energy storage, and it cannot have a runaway situation. How does it work? This is a very simple concept. It's my understanding. The electrochemists think it's too simplistic, but I'll still present it because many of you are not experts in this, electrochemists in this area. But if we look at, for instance, putting 2 carbon rods in a beaker of electrolyte, and to be concrete, let's talk about using salt water as the electrolyte. So it's an ion conductor and electron insulator. If we put voltage between the 2 rods, we get charge separation right at that interface. And if we open the circuit then, what we find is that charge persists. It's balanced exactly. We have ions from the electrolyte balancing the charge, either holes or electrons, in the solid. And this was discovered more than 100 years ago. And so it does provide charge storage of about 10 microfarads per square centimeter of surface area. And it's physical charge storage. There's no electron transfer. That's key for its high cycle life. No electron transfer, so there's no volume change, and there's no phase change involved. It's just bringing the charge up against the surface and then relaxing it. The voltage, however, is limited by the breakdown potential of the electrolyte, which is, for this example of salt water, would be about 1.2 volts. And high surface area electrodes are used there, and I'll show you that in a moment. But if we look at a cartoon of what this double layer is, and I took this from a textbook here, you can see that we're bringing ions up against the surface, and the separation between the charges is on the order of 1 nanometer. So that is really the source of the high capacitance. We get very, very small charge separation. Much, much thinner than you're going to get with a, for instance, an electrostatic capacitor where you actually have a film, or electrolytic capacitor where you're growing oxide This can be very, very thin right here. And so that's typical construction is shown here, where we have the two electrodes. Instead of the carbon rods, I'm going to use a high surface area carbon in the two electrodes. And I have a separator. Instead of the physical separation between my two electrodes, I'm going to bring them as close together as I can, and generally that's about 20 or 30 micrometers, and that is a single purpose separator that's used. It is just a microporous separator. It has no other function than to separate the two electrodes. We have two current collectors generally, and oftentimes for the organic electrolyte, these current collectors will both be aluminum. And if we look at the electrode material, the most common is activated carbon. And activated carbon is really high surface area. The example here is 1,500 square meters per gram, and that can give you 100 farads per gram. To get a feeling for how much surface area that is, 1,500 square meters per gram would mean 1 teaspoonful would be about the same area as a playing field. So it's really high surface area material here. And the practical devices are shown right here, and it's a jelly roll construction is the most common, and the carbon is coated on both faces of the aluminum current collector, and two aluminum current collectors coated both sides, and two separators are wound up. And this example right here is 3,000 farads, 3 kilofarads. And kilofarad is a good unit for this technology. Rated at 2.85 volts. This is kind of a state-of-the-art device. This is kind of the standardization now of 60 millimeters diameter. And this is approximately the largest size because of thermal management issues. You don't get ones larger than about this size. The response time is about 1 second for this product. This is showing picture of some small electrochemical capacitors, and I called your attention this one up here, CapXX, that is produced here in Australia. And that is a company that I believe is in the Sydney area, and they have been in business since the 90s making capacitors, and you may not realize it, but you probably have products that are using, for instance, cell phones that are using their products. And here's some other examples that's shown right here, different companies. This is the original one, was NEC Token, right here, aqueous electrolyte. And this is kind of a collage of large electrochemical capacitors. And it's shown right here from Japan, from the US, Germany, that's Korea. So there's quite a number of them. This is from Japan. This is an asymmetric. This is from Russia. That's an asymmetric capacitor also. So there's quite a number here. UNESCO is from the Ukraine. And so they're made all over the world. So let me just compare them now to help you in understanding the difference between electrochemical capacitors and something you're more familiar with. And if we compare it to a standard battery, which stores by chemical charge storage, and we have physical charge storage. And that has really impact on a lot of other factors that I'm going to have on the table here. The power limitation for a battery, of course, is reaction kinetics. That we have a reaction taking place, and that could actually limit the rate that we could charge or discharge it. Whereas the capacitor, it's just the conductivity of the separator. The energy limitation is the full mass on the battery, because we generally have bulk diffusion in a battery where we don't rely on diffusion at all for the capacitor. It's just the surface area. The output voltage is generally constant because we have thermodynamic limits. They're set. The potential is set by thermodynamics, whereas for the capacitor it's a sloping discharge, but that allows the state of charge to be known precisely. The charge rate, again, for the battery is limited by reaction kinetics. If you charge it faster than nature wants to allow you to do that, you run into problems, oftentimes safety problems. And for the capacitor, it's the charge rate can be just as fast as the discharge rate. And cycle life limitations or life limitations generally are limited by side reactions. That's impurities that might be in the, you want strict physical charge storage in these devices. You don't want to have any reactions going on, any chemistry, which will limit the reversibility in life. So if we look also at comparison of the energy stored, cycle life, and charge, if we look at lead-acid batteries, that is really one of the lowest specific energy. It's very common. This is what you use for cranking the engine on your automobile. It's also been used in the early days for photovoltaics. I don't think it's so popular today. But you can see cycle life is quite limited. It's a few hundred cycles. And the charge-discharge times are quite long. Generally, it's many hours. Lithium-ion batteries are certainly an advancement on specific energy, also on cycle life, and also the rate capability. Electrochemical capacitors have, as shown here, very high cycle life compared to the batteries. The response time is about 1 second, and that's to be compared with 10 to the 2, 100 seconds or longer, or 10,000 seconds. Electrolytic capacitors, as I showed you before, have even shorter charge-discharge times and much higher cycle life, and electrostatic capacitors. And one last column I wanted to show you is the cost relationship. And again, there is a correlation. The faster the response time, the more expensive it is. And lead-acid batteries might be $100 per kilowatt hour, $1,000 for lithium-ion batteries, $20,000 for electrochemical capacitors, but that's very low cost compared to electrostatic or electrolytic capacitors. So one point I want to make here, a major difference between the capacitor and the battery is during charging. And remember, we have chemical processes going on in the battery, and we have physical processes going on in the capacitor. What I want to do is an experiment of charging a capacitor in a battery from, for the capacitor, it's half its voltage to its full voltage, and for the battery, it's 10% state of charge to the maximum voltage it's allowed. And I'll do that at constant current at different values, so it's different charging times. And what I find is specific energy on charging the battery for long times has much more energy, specific energy, than the capacitor. And at, for instance, 1 hour, 3,600 seconds here, it might have 15 times more specific energy. But as time gets shorter, for instance, at 100 seconds, we can see that the battery is doing much poorer job of storing the energy, as the capacitor is essentially flat. And at 20 seconds, they have approximately the same specific energy. And at shorter times, the capacitor has higher specific energy than the battery, and this is during charging. But the full story is to look at the efficiency, and that is shown right down here. We have the capacitor, it's above 90% efficient at 20-second charge, and the battery may be at 60% efficiency. So for charging applications, you cannot beat a capacitor. So just to summarize this introductory part right here, we have extraordinarily high specific capacitance in the capacitor. 100 farads per gram is very common for the activated carbon materials. It's very high energy compared to capacitors, but it's very low energy compared to batteries. It's got low cell voltage, 1 to 3 volts, just like batteries, so you have to series connect them to make high voltage systems. The response time is about 1 second. So batteries they talk about a 1C rate and a 10C rate and so on. That's 1C is an hour rate, and we're talking about a second rate. So this is really powerful compared to batteries. They're expensive on an energy basis compared to batteries, very expensive. And as I showed you, maybe 20 times more expensive on an energy basis than lithium-ion batteries. But they're very powerful compared with batteries, and really unlimited cycle life in most applications. Most manufacturers will specify 1 million cycles minimum, but they'll operate well beyond that. Usually, if you do testing of cycle life, you wear out your tester rather than the capacitor. So let me just show a very simple comparison of different types of stored energy. This is 70 kilojoules of stored energy. This is 22 kilojoules of electrochemical capacitors rated at 2.5 volts. This is one flashlight battery or torch battery right here, alkali cell, and that is a teaspoon of sugar. All of that is 70 kilojoules, but it behaves differently and you're going to use it in different applications. So now let me talk about some of the energy conservation applications now. And first of all, I want to point out a simple equation from basic physics that the energy, kinetic energy, is proportional to the mass times the velocity squared. And what we show here is different masses versus velocity, and I have two different scales here, and the kinetic energy in kilojoules. For instance, if we are at 20 miles per hour, and we have, for instance, approximately 10 metric tons moving at 20 miles an hour, it's about 500 kilojoules of kinetic energy. The very first application of capturing that kinetic energy in a hybrid vehicle was performed back in the 90s, and this was by NASA in the US, and they used a city transit bus, and for this particular application they had 20 farad 400 volt capacitor system. And these capacitors were some of the earliest types of capacitors. In fact, they came from Russia. They were aqueous electrolyte, very powerful. They'd been developed in Russia for a number of applications, including starting of locomotive engines. So they were very advanced for what was available at that time, and nothing else was available commercially except in Russia. This particular application, they used capacitors because the batteries didn't have adequate life. The cycle life was not adequate, and it also, the state of charge was difficult to measure on the batteries. And there was also safety issues and so on. So NASA tried to implement this, and now I might say there are tens of thousands of city transit buses that have been hybridized with capacitors. So this is the NASA profile here. We accelerate the bus, and that's discharging the capacitor. You can see that right here. And here's the braking event, and this right here is charging the capacitor again. And the typical cycle, it might be, this is the White Book cycle that was used, 46 seconds. So this repeats. The bus goes block to block or bus stop to bus stop, going through this cycle, charge, discharge. And a typical life in this application might require 200 to 300,000 cycles. Here's another example of kinetic energy capture. This is an electric motor that's been put on the drive shaft of this small truck. And this is being used in applications, for instance, in airports for taking people to rental car companies or for parking lots. So it's a lot of start-stop operation. Another example is a train where the capacitor system is located on the roof. And again, one can see the savings, energy savings. Here, if the distance between stops is like 3 kilometers, it's more than a 30% energy savings. Now this is true even though this is tied to the electric grid. And that's because oftentimes the electric grid will not accept the power that you're putting into it, especially if two trains are coming in the station at the same time. This is a very interesting example. This is a Komatsu excavator, and that the rotation of the turret has been hybridized. That's the electric motor now. So it's still hydraulic for digging, but the swinging is done by electric motors. And that is using capacitor storage. So it swings the arm rapidly, stores the energy to stop it, and swings it back and forth, back and forth. And they're typically experiencing 30% fuel savings by this hybridization. And they're on their 3rd generation model now, so it's been quite successful in conserving a lot of energy. This is the largest example of hybridization I've seen. This is a Caterpillar. It's mining equipment, and you can see the people, the size of this device right here. It has 4,500 horsepower engine, but the machine power is over 8,000 horsepower. So it's taking 3,500 horsepower from stored energy. And that's actually done by 48 megajoules of capacitors. And this is 4,700 cells of the type I showed you there, 3,000 farad size. And they're talking, or they claimed 25% fuel savings over the non-hybrid version. And it does the energy capture when the boom is going down, and also when it's swinging when it stops it, because every time you stop something, there's a chance for saving energy, storing the energy rather than just having it dissipated. So there's also an energy of location. If I lift the mass up, the equation that defines the energy stored is the mass times the gravitational constant times the height I lift it. And this is one example here, these seaport cranes. These are grid tied that unload the ships, but once that container is removed from the ship, it uses these rubber tired gantry cranes. And these move around an awful lot. They load trains, they load trucks, and they stack, and they do a lot of movements. You can see how big these are. There's people down here. And this has been hybridized because it lifts and it lowers the same mass up and down. Every time it lowers, it can save that energy, store that energy, and have it for the next lift. And this is an example of the results that were achieved here. By using stored energy, they were able to reduce the power of the engine in the hybrid system. The engine size went from 14.6 liters down to 11 liters. And the generator capacity was almost 1/2 because it can use stored energy in addition to the electric power. And they're claiming 38% savings of energy by hybridization. They're using the capacitors. So let me talk now briefly about the energy sector applications. One existing application that's quite popular is emergency pitch control of wind turbines. And this pitch control right here is shown just by rotating the blades. These are very large blades and big wind farms. I'm sure they're all over Australia. I haven't seen them yet, but I'm sure they are. But in the hubs of these, they have electric motors to feather the blades if they lose power and it's an emergency situation. They're using stored energy. And the capacitors are very popular. Because they are reliable, they work at low temperatures, and they have a lot of real advantages. They're maintenance free, and these towers typically are 100 meters tall or taller, so that's not a fun place to walk up to change batteries if you need to do that. So they are also very safe and have high power performance, and the motors typically are many horsepower that do that emergency pitch control. So this application is one that in recent years has used the number volume of capacitors sold probably went to this market. It was one of the largest. Here's another example. This is a grid-tied UPS system, and this one provides 10,000 kVA, but only for 1 second. So this can power a whole factory for short times. And you say, well, why would you want to do that? Well, if you have a very automated factory with high value manufacturing, even 1 cycle loss going to that factory will cause your robots to stop because you don't want to have them cause any problems. And so they'll go to their neutral position. And so this is what's been done on some of the wafer fab facilities. In Japan, it's more common, and one in the US, I'm aware of one. But you can see right here, they have a voltage drop, and this is data from Maiden in Japan. And what they see is that the voltage and current is maintained right here. And you can see the capacitor is discharging and the current is going up as the capacitor is discharging. But this provided 0.4 seconds of backup. So that the factory would have stopped operation with this voltage drop right here had not it had this backup system. And why do you use capacitors rather than batteries? Because you can count on them. They're reliable. And they're much more expensive, but they pay for themselves in this application. Very, very safe operation, high reliability. You can count on them to do the job, as I mentioned, and also very high cycle life. Although oftentimes these short-term glitches aren't that common. They might be, a few times a week, depending on the quality of the power that comes to the electric grid in your location. This is an interesting application for the electric grid. This is Arapahoe in the U.S. This is a solar tracking system. It has all these mirrors. You can see it. This is a photograph of the 3 mirrors. They have towers here where they shine all these mirrors, the sunlight on, and then they generate steam and generate electricity from that. And this particular system right here has 300,000 mirrors, and they follow the sun from sunrise all day long until the end of the day. And these mirrors each have to have stored energy, because at the end of the day, when the sun is disappearing, they need to swing back and be ready for the next sunrise. And they have to have stored energy in case wind comes up and they need to go to a neutral position. And the capacitors are being used for this application for controlling the mirrors. And again, this is much simpler than other stored energy, and it would be a nightmare to have wires strung to all 300,000 mirrors. So you want to have them each independent. This is taken from 1 month in April 2010 by the Bonneville Power Administration. It shows the wind, which is the the wind is the blue, and you can see the wind is up and down every day right here throughout the day. It also shows the solar power, which again has a lot of hash in it, and the averages are shown right here in the middle, and the wind average is shown here, and the demand is the red. And you can see that there's large fluctuations. So if we had the ability to store energy, we would make the wind and the solar more valuable. We could better match the generation with the demand. And one report that was published a number of years ago that I find very useful came out of Sandia Laboratory. It's a Department of Energy laboratory in the U.S. And this, although it's a little bit dated, it does talk about the economics. It talks about the benefits of grid storage in a lot of applications. I think there's 23 applications. And so I recommend this report. It is available at no cost on the internet. So you can get this report if you're interested. But I want to talk about day-night storage, which is discussed in this report. And for the normal, this is very simplified, minimum demand, middle of the night, and peak demand. And as I've learned at this conference, usually you have a double peak during the daytime, in the morning and then the evening. But this is very simplified. What you can do with storage, if I could store energy at night when I'm still generating it and cut off the peak right here, that would make things a bit higher utilization of my generation. And if I had if I had 1 cycle per day, 5 days a week, that for 20 years, that would be about 5,000 cycles. So I don't need high cycle life, but 5,000 cycles is much more than you're going to get out of many storage systems. But for electrochemical capacitors, it's very doable. And the day-night storage is used with the electric power grid, and the mass and the volume of that storage system are really not very important. Really what's important is the cost of the energy storage cost. And oftentimes it's quite low rate. You'll be charging it over 5 hours and discharging it over 5 hours. And it must compete with new power generation to be effective, because otherwise you'll generate more power than store the energy here. And really the important metric is this cost of storing energy, dollars per kilowatt hour on here. And as I mentioned earlier, the most popular storage is pumped hydro, and that's 98%. This was from the year 2010. And all this small sliver here of the 2% is comprised of a number of different technologies. There's no capacitors in there right now, I might say. But pumped hydro, as you all are aware, is just lifting water uphill and coming back down. And again, it's physical storage. It's the MGH. And there are a lot of applications around the world. I noticed that from this list I took from Wikipedia that there was one system in Australia that was on the list, and I took a picture of that. I believe it's south of Sydney. I'm not real sure of that, but it's, they said it was the first pumped hydro system in New South Wales. But what I want to do is talk about this asymmetric aqueous electrolyte capacitor. That has potential for competing in this day-night storage. And as I told you before, the symmetric capacitor has both electrodes the same. The asymmetric capacitor generally has different materials in the positive and negative electrode. Generally, it'll have one electrode that's got a Faraday process and the other one double layer charge storage process. This is the symmetric design. Both electrodes are identical. For the asymmetric, if I have a Faraday, it stays pretty much at constant potential, and it's only the one electrode that is changing with charge. And the nice feature here, it's much lower cost than the symmetric design. Showed you very expensive symmetric, but the asymmetric with aqueous electrolyte can be very competitive. The name actually came from a Russian group that in a US patent where they have an asymmetric electrochemical capacitor and method of making. And this group right here fielded bus in Moscow in the mid-90s. And this was an electric bus completely powered by capacitors. No batteries, no engines, just capacitors. And they also had a truck right here. And more recently, there are buses being used in China that using the same technology. It's a nickel oxyhydroxide positive electrode and an activated carbon negative electrode. So there's some important characteristics of asymmetric capacitors, and its response time is a bit longer, but for a 5-hour charge and discharge, it's not a disadvantage. This is the one that I think shows potential for the electric grid, and this is from, again, the Russian company Elton, and they're using a standard lead positive electrode with activated carbon. And they show some cycle life here, 5,000 cycles. Out here. And just to show you what I believe would be important is if we have a decommissioned power plant, and there are many of these in the US, they will actually take all of the valuable components out of this and leave just a shell of a building, but they usually have an empty building, but they leave the switchyard intact. And they usually don't decommission it any further than that because it's very expensive. They have a lot of site cleanup and so on. So this particular, if I wanted to use that as an example, I'm going to fill that volume inside there with capacitors. And let's see what I could do. And it's roughly 100,000 cubic meters. And if I use that lead carbon capacitor at 50 watt hours per liter, I have the ability here of storing about 5,000 megawatt hours. So that would be 1,000 megawatts for 5 hours. And I want to compare that to a common pumped hydro system. This is actually Raccoon Mountain in Chattanooga, Tennessee in the US. And they have a 305-meter lift from the Tennessee River up to this reservoir. And they empty it and fill it every day. If we had a capacitor system, it would be much smaller, and I wouldn't need the mountain. So for the day-night storage, I think the electrochemical capacitors offer potential right there. I think our projections are less than 10 cents per kilowatt hour of storage cost. So they have potentials to actually be an improvement over other technologies. And the mountain and the water are not needed. Storage economics, I'm running out of time here a little bit, but let me briefly run through this. Again, this example, for people that attended yesterday, I went through the same example. It's looking at a kinetic energy capture on a bus. And if I put value of 15 cents a kilowatt hour on the electricity cost, and I have kinetic energy right here of that moving bus that's moving at 33 miles per hour, I have about 8 cents of value. And if I look at efficiency, I only have about 6 cents of value in that moving bus. So if we look at the application, 1,000 cycles per day and 333 days a year, we have about $20,000 cost savings potential if we were able to capture that energy and reuse it. And the capacitors sell for less than that price, and they have much longer life than 2 years, so it looks interesting. If we now look at a battery, the battery has the same situation. It's used in the same bus, 8 cents, but now I have 4 cents that the value because I have a little less round-trip efficiency. The annual savings is a little bit less, 13,000 versus 20,000, but the capacitor cost is so much more than the battery. The capacitor is 17,000, the battery is only $750. However, one must have a limit on the charge rate of the battery system, so they only can change that by 5% state of charge, so we have to have 20 times larger battery. So we have to supersize the battery in order to make it work here. And so that brings the price very comparable. And the life is only about 2 years for the battery system, so the capacitor is, it certainly offers advantages over the battery in this application. The last point I want to make is the energy stored on the energy embedded in the system. And this was taken from a paper a number of years ago. There's been two subsequent papers that are discussing this. And you can see the higher this number, it's the more value you get from your storage system for the grid. And so for the compressed energy storage, I get 240 times more energy out than it took me to build that system. And so this analysis was done. This is from a group at Stanford University. And the second one is the pumped hydro system is very high, but lead acid battery they have here is very, very low, 2 or so. But the analysis, they say, is increased cycle life is the most effective way to improve your utilization efficiency, to actually have more return on your energy investment. And so if we take the 2 for the lead acid battery, and if we have the cycle life going from 300 cycles up to 3,000 or 6,000 cycles, we can make the capacitor look very interesting compared to the alternate technologies here. And that includes a vanadium redox battery and lithium-ion batteries. So the capacitor looks attractive from this standpoint. So let me just summarize by saying that the capacitors have very attractive features: cycle life, reliability, and the maintenance-free operation. They also have been used for entire factories, UPS systems. They've been for capturing energy, tracking mirrors, and they have good potential, but they're not being used currently in day-night storage. And they're also fast regulation of the grid. They have that potential, but they haven't been used. So I just want to end by saying that there are many, many places to get more information about this technology. It's been around, as I mentioned, since the commercially available since the 70s. Right now, there's dozens of manufacturers around the world, including here in Australia, and the technology is still growing. Double-digit growth, and I think it does serve useful purposes. So let me end at this point. Okay.
I think we've got time for a few questions.
Thanks very much for that very interesting talk. You mentioned that it's not used as widely as perhaps you'd like, but yet there are compelling economic arguments for using it. What are the barriers that are causing it to not be used as much as you think it should be?
It's not being used. I think part of it's education. People don't have an appreciation for what the technology offers. I think this is a good forum to help with that, so that people can see, yeah, there's areas that I might be able to use this. But I think education is one thing. People have the opinion that capacitors don't store much energy. Even the electrochemical capacitors are not much storage compared to the batteries, but they do seem to have a good fit with a lot of industrial applications, including transportation.
My understanding is they are costly compared to batteries or compared to other capacitors. Where's the cost driver?
I think the major cost driver, and you're referring to the one, let me see if I can find this slide here. They are very expensive compared to batteries on an energy basis, but they're cheap compared to conventional capacitors on an energy basis. And you can see the price right here, $1 million per kilowatt hour for an electrolytic capacitor. It's only $20,000, but that's much higher than the lithium-ion battery at $1,000. I think the major driver has to do with purity. We expect very long life out of this technology, and side reactions have to be eliminated because they'll limit life. And side reactions means that we almost need semiconductor level purity in the materials that are used, because they will limit life. They will react, and you don't want that to happen. You need good packaging too, so once it's sealed up, that you don't get water in it or oxygen and other things that will react.
You mentioned that an application for day-night storage is very applicable for electrochemical batteries. What about longer-term storage? What sort of decay rates are there for the
Decay rate for the asymmetric capacitor is quite low, but I'm of the opinion that you need to cycle them in order to have value. I would use a different technology if you want longer-term storage, because it's very expensive on an energy basis. If you don't cycle it, it's going to be very expensive.
That's where you gain with the cycle.
Yeah, it's like I showed you this bus example. If you didn't have 1,000 cycles a day, for instance, if it's your automobile, where you had 2 cycles a day, the economics don't look very good. You need to have something in use a lot and a lot of cycling.
But similar question, but applying to the UPS applications where the charge has to be held for a long time. Well, it could be, depending on when you're going to use it. So there it's a security as applied that's important, isn't it? Will that decay away, or do you use it in a configuration where you're having continuous charging?
It's continuous charging. It's grid tied, yeah. For the example I showed you, let me see if I can find this one. It is actually, yeah, right here. This is actually grid tied, and you'll have the power keeping the capacitor charged right here. And then you have a fast switch, and then you use the stored energy right there just when you need it. So the self-discharge is actually quite low, so they're actually, you don't need to trickle charge your capacitors. Once they reach the voltage, they just stop drawing. It's at lower cost than the battery, for instance, to hold them there.
Yeah, oh, I see, okay. Thanks.
Thank you, Professor. So after your seminar, I understand that the biggest advantages of the supercapacitor is unlimited life and a high response time. But as far as I know, the medium results flow battery also has unlimited cycle life and a very fast response time. So how do you compare these two?
Okay, I'm not as familiar with the flow batteries as I am, but I think whenever you have moving fluid, you're going to be slower than something that is almost instantaneous. 1 second is the response time for the capacitor. And if I had to start and stop motion of fluid, I think that's going to be longer than 1 second. And so the response time is going to be a bit different. And the second part of your question was?
And the cycle life.
the cycle life, million cycles generally for these symmetric devices. Flow batteries, I think you probably have, again, side reactions limit the life. You know, your constituents don't wear out, but you have corrosion and other problems that might be limiting of the life on the system. But I'm not an expert in that, flow batteries. I don't know much about those. I'm just suggesting that there might be other mechanisms you have to look at.
And one more small question. So is there any maintenance costs or other required periodic maintenance of the supercapacitor?
Generally, no maintenance is required. You install them, and generally they're welded in a system so that you have no problems with loosening of connections and due to vibration and that sort of issue. But they're welded in, expected life have a life longer than the application. So these buses that they're being used in are 12-year life. The capacitors last longer than the 12 years.
Maybe last question?
Did I hear you right that the projected cost for the asymmetric aqueous electrolyte one was 10 cents a kilowatt?
That's what they're talking about. Yeah, it's $300 to $450 per kilowatt hour storage. I mean, they're actually and cycle life better than 5,000. So I think it's going to be competitive. I think it's in the realm that looks interesting. And there are some problems. I know the Elton Company was very active in this area, and they were solving some side reaction problems, corrosion problems. That might limit the life. You know, the capacitor will do its job, but you got to package it.
Okay, we might stop there. So thank
Okay,
you. Thank
okay.
you very much, John, for your very interesting talk.
Thank you. Okay.